In this video we will learn how to develop a plugin or a protocol for Scipion. So let's start with what we want to do. So we start a new project. So let's call this course development day 2. And then we have an empty project, and for this project what we will develop is are two protocols, one for filtering a volume, the other one for subtracting volumes. And just consider these two steps as very simple steps that we do just to learn how to program protocols, not just to do something really useful. Okay, so the first thing we will need, as we want to filter a volume, is to have a volume. So we have an empty project, so we need a volume. So let's look for PDB. So here we have convert a PDB. So from XMIP, so we can click on it, and we can take the PDB either from the PDB database, from an object inside Scipion, from a file. So let's take it from the PDB database, and here you can control what is the final pixel size, what is the final size of the volume, and so on. So let's modify this. Let's call it 6VSV so that we see in the label which structure we have included. And now this is a model of the coronavirus SARS-CoV-2 spike. Okay, so here what we have is a volume of size 195, and we can have a look at it, and we see that we have the different slices, and hopefully this works. And here we have the structure of the coronavirus spike. So our goal now is to filter this volume, and for that we will construct a protocol that we will put here in pre-process. We have here a couple of protocols. We have here the two that I will use during the course, that are the filter volume and subtract volume. So we will see how to construct this one, and then the exercise will be that you construct the second one. Anyway, the second one is also solved. So if you move to the right branch in the Scipion EM template plugin, you will have access to all this code. And okay, so let's start with the first one. So with the first one, what we want is to have a volume to filter. So I will take this one. We can have different filter shapes. So we can have a Gaussian that is defined in real space. So this is the sigma, and this sigma is in voxels. So here, for instance, we see that the sigma of the Gaussian in voxels. And then we can also define a filter in the Fourier space. And then we have here the cutoff resolution in angstroms. And when you execute it, so let's do it with the Gaussian, for instance. So we do it with the Gaussian, it has finished. Now we can analyze results, and well, let's see it more. So we can either click on the object. So the object is just the default viewer for this kind of objects that are volumes, and then it should be a filter version, a low pass filter version of the previous one. So we can see that we have performed a low pass filter version of the previous one. We see many less details, and also just for the purpose of for the sake of illustration, we have provided a special analyze results and a special viewer to this protocol, and this special viewer opens two things. One is the filtered volume, so it is the same as the one we have already seen, and the other one is the difference between the input and the filtered volume. So this is the high frequency component that we have lost in the during the filtering. So here you see all the details that we have lost in the filter volume. So okay, so the practice is about how to construct all these, and for doing that, let me go to here. So let us open how to construct a workflow. Okay, so we can start full screen. No. Sorry about this presentation. Okay, so how to develop a workflow. Okay, so the first thing is to create a file that will contain your workflow, and this file has to be for instance, here it is in the Scipion EM template plugin. There is a folder called my plugin. This is how Scipion will see your plugin from the Python code. And then inside my plugin there is a folder protocols, and then inside that folder protocols you define your protocol file. And this protocol file needs to a file name, a class name. So normally we have the convention of starting with the name of the plugin and then whatever operation you want to do, and it has to inherit from EM protocol. That is a class that you can find here in PWM protocols protocol. So you inherit from EM protocol, and then you have to give a help and also a label. So this label is the one that appears when you call it from here. So filter volume. So here you always have the name of the plugin and then the label that you have executed. You may change that if you want. You can add whatever you want there, but otherwise the default labels will appear there. Okay, so then let us go presentation again. So the two important parts are create the file, give the class name, write the help, and the label. So next is to register this protocol and to let Scipion know that this protocol exists. And to do so, you have to edit the init.py inside the protocols folder. So this init.py, what it has is a link. It is an import to every protocol that exists under the plugin. So if you create the file but you don't register it, then you will not be able to access the plugin from Scipion. Okay, so and this is just from this file import my class. And then also it is convenient to put it on the menu, on the left menu of Scipion. So this is this place here that we saw it before. Let me close this one. So to put it under 3D preprocess and then my plugin or my protocol. So to do so, what you have to do is to edit a file that is called protocols.conf, and then in this protocols.conf you have to say in which view you want to save. There are different views. For instance, there is one for single particle analysis, another one for tomography, another one for model building. So you have to specify which view you want to include it. You can include the same protocol into multiple views if you want, and then inside that view you have to decide in which section, this is the 3D, and which subsection, this is the pre-process, and then there you have to create this line. So this line says I want to have my protocol under this section with the default label, and the default label we can see where is it here. The default label is the one that you have chosen. Sorry, that you have chosen here. So before we define our label, so this label will also go into the menu. You can also give a specific label if you want, but using the default is good normally. So first step is to create the file, write the help, write the label, and change the class name. Second is to register this protocol into the Scipion environment. And then the next step typically is to design your form. So you have seen before that in our form we will ask for a volume, we will ask what kind of filtering you want to do, and what kind of what are the parameters. For instance, if you apply a Gaussian filter, what is the sigma of that Gaussian filter? So let's start with the easy things. So there is a section, a routine that is called define params. This is part of your protocol. So in your protocol file, you will have this define params that is overriding one of the methods in EM protocol, and then there you have to add the form. And it is very important that, so you receive the form, you add something to it, and then you return it at the end. And it is very important that you add sections. If you don't add sections, no matter how many parameters you add, they will not go into the form. So first you add a section, and then you can add your parameters to this section. And here you have some examples. So let's start with the easy ones. So the easy ones, let's say that this float param, this was the one with the Gaussian. So let's say that I want to add a sigma parameter. So this is the name of the parameter inside the program. This is the type of the parameter, so that in the form we offer some box so that you can type a float number, and there are some small verifications that what you have written there is a float number, it is not a string, for instance. And then this is the label that will appear in the form, so we can see it here again. So let's see how it appears. So this is the label, sorry, this one, Gaussian sigma, and then this is the help. The help is when you click on the question mark, you get the help, and you have specified that in this with these arguments. And you can also even define default parameters. So if you don't give default, it is empty, and then it is requested from the user. The user is forced to give some value there. So this is an easy one. You can also make some parameters advanced. So for instance here, this one is advanced. So that means that by default it is not shown, but it can be shown under the advanced option. So for instance here, we can see if I choose raised cosine, then I don't see an extra parameter, but if I go to advanced, then I see the transition bandwidth. That is it is a little bit more difficult to choose, and that is why it is advanced. It is defined in radians per voxel, so that means that is a digital frequency that is normalized to 0.5 at Nyquist. Yeah, so this parameter is more difficult, so that is why I have put it as advanced. But this gives you the idea that you can put many parameters in your form, and some of them, the most frequent, you can ask the user, but the most difficult ones and those that are meant just for specific cases, you can put them in advanced. Okay, so let's continue. So let's see what we have here. Presentation. Then next thing is that you can also define a list. So we have here this example of choosing a Gaussian or raised cosine. You already saw it here. So when you open, you can choose from a list Gaussian or raised cosine, and then the way to do that is you go you define one of the parameters as an enumeration param, and this enumeration param has a number of choices, Gaussian of rise cosine, and these choices are numbers. So this is number 0, this is number 1, and it is a good practice to put names on to 0, 1. So we put shape Gaussian, shape rise cosine, and we assign the values 0 and 1. And then we can define what is the default. The default is 0, so that is Gaussian. And then you can also put conditions on the rest of the parameters. So for instance, this parameter, this Gaussian sigma, only makes sense if your choice is Gaussian. So you can put this condition in the definition of the parameter in the form. So you can say condition filter shape is equal shape Gaussian. So that is, if you have chosen filter shape equal Gaussian, then this is shown. Otherwise, you can see that these two other parameters, they are kind of conditioned to having selected rise cosine. And be aware that when writing, this condition is evaluated at some point, and the evaluation doesn't involve self. So it is not self dot shape Gaussian. That would be the right syntax in Python, but this is not Python. This is Scipion evaluating it. And then let's see some other kind of a bit more advanced parameters. So we can have the volume. The volume is a pointer param. It's a parameter that is pointing to a volume. And then among all the objects that we have in the project, so at this point we don't have many objects. We have only volumes. But when we look for, when you press on the magnifying glass to look for an object, you are only offered objects that belong to the class that you have chosen. So I have chosen here volume, so I'm only offered volumes. And you can also put several classes. So if you separate by commas, so you could put volumes, comma, set of volumes, comma, whatever you are interested in. And then, as this is a pointer, this parameter is important. So whether this pointer can be empty or not. So if it is the main entry, it cannot be empty. So if you want to filter a volume, you have to be given a volume. But let's say that this is pointing to a mask. And sometimes the mask is used. If you don't give me a mask, still I can do my operation. So then you would say allows null equals true. Okay, so these are pointer params. The next thing is to create an execution plan. So remind that in Scipion, the planning and the execution are separated. So first you define which are the functions that you will execute, but at this point you are not executing yet. And then you give this plan to the workflow engine, and then the workflow engine will execute it. So at this point we are creating the plan. So the plan is created in a function called insert all steps, and here you have there are a few choices, but the most common one is insert function step. So that means the next thing I want to execute is a function that belongs to my class. So it is the function filter step, and it has an argument that is the object ID, and we will see later what this argument is meant for. And then once you have executed filter step, I want you to execute create output step, and here you have the create output step. So what is this argument? So this argument is meant to allow Scipion to decide when you have to re-execute a step. So this filter step is applied on a volume. So let's say that you open the form again, change the volume, and click run. So if you rerun the protocol, some of the steps may not need to be re-executed because they will give the same result as before, but you have changed this parameter, and then from this parameter all these steps would change. So here we could put all the parameters that are related to the filtering. So we normally tend to put mostly the objects. So we define the re-execution based on which objects you are processing. But it is true that if you want to be pure, then you should also add the parameters of the what is the filter you have applied, what are the parameters of the filter, and so on. And if you don't want to be so pure, the simplest thing is that if I want to rerun this on a different volume, then I click restart, and then this will restart the protocol from scratch. But otherwise, if you want to be more precise and only re-execute part of the protocol, you may use these arguments to define what are the data dependencies between the steps. Then let's implement our function. So the first function to execute, the first function to execute is this filter step. So let's implement it. So the first thing is to grab the volume. So we have a parameter that is input volume. So this is this name here. So we have input volume in the form. So I ask you for the self dot input volume, but this is a pointer. So to get the object it points to, you have to give get. And so up to input volume is a pointer to a Scipion volume. When you do get, what you get is a Scipion volume. And this is about pointers. The next thing I would like to highlight is how to deal with file formats. So typically, nowadays most of the programs can deal with many different file formats, but some of them, they are written in a way that they only accept particular file formats. So for instance, let's say that this is not the case of XMIP, but just to illustrate the how you could do this, let's say that you want to write your volume as an MRC file and for processing it. So you have a class that is called image handler. This image handler is the class that knows how to deal with images, volumes, stacks, and how to make conversions from objects to files and so on. So you define an instance of the image handler, and then you define where you want to write the file, and we will talk about this a little bit later, or just in a moment. And then you convert this object, that is a Scipion volume, onto this file. And you can create files in three places. So you have get path, get extra path, and get TMP path. Okay, so let's see what that means. So when you run a protocol, you have a directory only for your protocol. This directory is under the project. This is the project directory. This is the project directory. And then in the project directory, there is a runs directory. And in this runs directory, you get a directory for your execution. So we see here that we have a convert PDB and a volume filtering. And if we look at every object, every protocol execution in Scipion is assigned a number. So this is number 2, this is number 45. You see there in the ID. So that is what we have seen here. So in the runs, we have one protocol, one directory for execution 2, one directory for execution 45. Inside each runs directory, we have a fixed structure. So you will always have a logs. So that is where part of the housekeeping databases for executing are stored. This is the RunDB and the steps SQLite. So this is internal for Scipion, but you also have the standard output of your protocol, the standard error, and some logging. And we will see now what these things are. And you also have two other directories, one that is called extra and one that is called TMP. So things at TMP will be deleted at the end of the protocol, so you don't have even to remove them. So when the protocol finishes, everything that is at TMP will be deleted by Scipion, and in the extra you can leave whatever you want there and it will stay. And then the convention we normally have is the main output of the protocol should be at the runs directory, so it should be at this level. So that is why the filtered volume should be at this point. And then in the extra, you put objects and files that are somehow important to keep. So you don't want to delete them because they may contain important information about how the thing was executed, or some internal calculations that you don't want to erase. But otherwise, those are not the main outputs. So the main outputs normally go to extra. Okay, so let's look at the execution. So at the execution, we have a bit of, so we have a logging by Scipion. So in this logging, we have in which machine you are, which is the version of the pipe workflow, what is the current directory, the working directory. So there are many information. There is a lot of information just before starting the protocol. And then you have when the first step in the plan started, it started at this time, and then it finished at this time, and then we started the second step, and then the second step finished, and then we are cleaning the temp folder, and we have finished. And also you have the same or kind of similar information in the standard output. So in the standard output, what you have is almost the same. So where you are, and then which step you have executed, but then here you have a bit more. So we are running this command, and we will see how this we got this command to run. And then if this command is printing something, it will go into the standard output. If it doesn't print anything, then this part will be empty. For instance, this one, create output, doesn't print anything, and then we only see that it starts and finishes, and that's it. And so this information of the login and the standard output are the ones that are here in the logs. So you have the run standard output, the run standard error, and the run log. So we have this information, and even with the color codes and so on written in the file. Okay, so then we are here. Let us go to our presentation. So we are here in the presentation. So we have written the filtered volume in the get path. Get path is the runs directory, and now you understand these are the two functions. Get extra path, that is giving you the path to a file located in the extra directory, and get TMP path, that gives you the file name of a file located at the TMP directory. And so at the moment we are only converting whatever is the input file format. So we have a volume in whatever file format, and then we are converting it on or to MRC file. So for the moment we haven't filtered it. So let's filter next. So for filtering, you can do the filtering inside the Python function. So either you do your logic of this step at the level of Python code, or you do a system call. And to do a system call, the most typical one is this one, is self run job. So self is your protocol, and the reason why you need to do self run job is to keep all this logging of when the program started, what are the outputs, and you can also, this self run job, you can control also the number of threads, number of MPIs, and so on. And so typically it would be a program and then args. And it is better to use this self-run job than using the standard Python tools to invoke the command line. And also this self-run job can help you to set up the path, the LD library path. There are ways of giving an environment for the execution of this program. And this is a special case. So normally you would use self-run job and you would take care of all these path, LD library path, environments, and so on within your plugin. But this is a special case because we didn't want to write at this moment, at day 2 of the course, we didn't want to deal with that. So we are relying on some other plugin to handle all these path and LD library path things. So we are relying in this other plugin. So from xmip3 import plugin, and we give a name just to realize that it is the xmip3 plugin. Okay, so instead of self-run job, we will do xmip3 plugin run xmip program, and then we give the program and some arguments. And here in the arguments, you have to prepare, you have to read whatever is in the form and prepare the arguments for the execution. So this is actual execution. So we have to distinguish between setting up the plan. So the plan is simply constructing a graph of which function will be called after which, and this is real execution. So at this point, the file names and objects and even the directory, this 45 directory associated to the execution, doesn't exist. They don't exist. So they only exist when the graph is executed. So when it is executed, at this point, now it is executed, and then all these steps are executed at this point. Okay, so we construct the arguments, and for the arguments, what we need is, okay, give me what is the file name I have to filter. So it is the one we have just written in the directory of the run of the execution. So we take this name, and then what is the filter shape? So if it is a Gaussian, then I will add to the arguments these parameters, and if it is a raised cosine, then I will add these parameters. And there are a few comments we can do here. The first thing is that these are the parameters that were defined in the form. So this, for instance, cutoff resolution, that was a float param. So float param is not a float. It is a complex object defined by Scipion, so I cannot use those complex objects to make divisions, for instance. I cannot take the sampling rate and divide by this complex object. But if I do get on the complex object, each one is returning something simple in Python that makes sense. So for instance, if you have a float param, you get a float. If you have a string param, you get a string. And if you have an int param, an integer param, you get an integer. So now you can use those floats, strings, or integers in the standard way of Python. The other thing is that these complex objects, they have re-implemented the string percentage operator. So you can use them without the get. You can use the get too, but if it is convenient not to use the get if you want. And you can pass them to the percentage operator, so they know how to convert themselves into a string, and so that they can fit in the final string you are constructing. Another thing that is shown in this example is that this volume, that is a Scipion object, has some properties that you may query. So one of them, for instance, is getting the sampling rate. The sampling rate is defined in angstroms. So you get a float that is this sampling rate of that volume, and you may use it for whatever purpose. And the last step, typically in most protocols, is the create output. So in the create output, you have to so you have in the calculation step, you have produced this file. So you have actually filtered. So first we copy it without filtering, but then we have invoked this program, and here now you recognize how this was constructed. So this is the program name and then the arguments. So we have constructed the arguments to filter that volume, and the way this program works is that it takes the input volume and modifies it. And then, but this is a file that lives in this directory, but it's not yet a Scipion object. So we have to construct a Scipion object that points to that file, and that will be the output of this protocol. So will be this object that is coming out from the protocol. So the way to do that is here. So we can see it here. So we first of all we have to be ready for possible failures. So let's say that the program I'm invoking creates or doesn't filter it because of any reason, that it doesn't like the input volume, so it doesn't produces any output. So I should be prepared to these situations. So I should check first whether something exists, and otherwise do not do anything. And then here what I'm doing is constructing an object that is a volume. We point to the file name that is in the get path with that name, and it is a complex object. So this complex object has other properties, and Pablo will talk about the copy info properties. And here we are just setting the sampling rate. That is one of the most important properties of the object. So we get we set the sampling rate of this new object as the sampling rate of the input volume. And once you have constructed the object, then you define the outputs for this protocol, and then you say the output that is called output volume is equal to this volume object that I have just constructed. So the label output volume is chosen by you, and we try to keep the consistency between the names of the output objects, so that here, for instance, here you can see we have converted a PDB into a volume. The output is called output volume. We have filtered the volume. The output is also called output volume, but the name is arbitrary. You can put whatever, but if you keep the consistency between protocols, it is easier for the users. And then we have here the defined relationships. So we have in this protocol, we have taken an input object and we have produced an output object. So we inform Scipion which are the parents of the output objects. So this input volume, and you have to point for this function call, you have to point to the object, not to the pointer. So this object input volume get is the parent of the volume that I have just constructed. And then Scipion will also keep a graph of which are the parents of each one of the objects, and once you point to an object, it knows automatically all the objects that gave rise along the history of the workflow to that particular object. And so in principle we would be done with our protocol. So we have done the functional we have implemented the function of the protocol, but then there are a number of support functions that are useful. The first one is the summary. So the summary normally is a protocol is a summary of what the protocol has done. And remember that in this summary you will always have the input and output objects will be linked. So for instance, this is taken from a different protocol, sorry, but you see that the input objects were these, the output object is this one, so you didn't have to repeat that into the summary. So in the summary you have just to say what operation in a very schematic manner, which operation you have performed. And then, so for instance, we can see so in the summary what we have said is we have applied a Gaussian filter of sigma equal 2 voxels. So when you move to different boxes, you get a very quick summary of what was done. You can also write an extended summary. So this extended summary is something that is meant to be collected into a kind of methods or first version of the methods section of a paper. So you can say the volume, this one, and this funny name is the one that has, so this output volume has a unique identifier that is this one. So the volume, this was low pass filter, and then you can give a reference to say what a low pass filter is with a Gaussian filter whose sigma was 2 voxels. So this is a more verbose summary of what you have done, and then here you have the references, and even something very useful is you can select to here, and then you can see the methods, the concatenation of all the methods. So the convert PDB method didn't produce this extended summary because the programmer was lazy. But if you have the methods of all the protocols up to that point, then they all appear here, and then it is relatively easy to start converting this into something more human-like text. And so you have to give these support functions. So these support functions are called summary, so this is the short summary, and methods. And the way to do that is you construct a list of sentences or a list of messages that you want to give back, and then you add more and more sentences to that list, and they are shown on the screen. And that is nothing really new here. The thing that is new is making references. So for the references, you need this syntax in the string, so double brackets, and then these double brackets in your function. You need another support function that is in your protocol. You need another support function that is the citations, and then in these citations you have to give a bibteg index or a bibteg key, and in your plugin you will have a bibteg file, and this bibteg file is a collection, is a big string mainly, where you have all the keys, and you can use relatively standard bibteg syntax. There is some constraints. For instance, we are only looking for the journal field. So even if it is a book, then you have to give it as a journal, because otherwise it will not be shown. So if you just give the title, that would be the standard in BibTeX, this title is not shown. So so in these extended summaries, you have references. These references have this syntax. This syntax has to be also complemented by a function in your protocol that defines what are the BibTeX keys that you need. And these BibTeX keys have to be expanded in the BibTeX file of your plugin. And then also how to get this unique identifier for an input object. So there is a function in the protocol that is getObjectTag, and this getObjectTag either gets an automatic label as the one we have seen, or you can also change it. And let me see if it works. This is online, so I can edit and say my label is a spike or SARS-CoV-2 spike atomic model, and then hopefully this will. So the volume SARS-CoV-2 spike atomic model was low pass filter. So this function presentation. So this function either gets an automatic label based on what is the identifier of the protocol execution and then some automatic names, or it is something that the user is giving and that is propagated throughout the project. And then there are some other useful validation support functions, and one of them is validate and the other one is warnings. So I have borrowed these two from other two protocols. So in this protocol, what we are checking is whether this is the practice that you will do today. This is you are subtracting two volumes. Those two volumes have to be or need to be of the same size. So we get the dimensions of the input volumes, and then we check whether they are equal or not. And then if they are not equal, you cannot perform the subtraction, and then we stop. So before launching, Scipion is making this, is calling the validation routine of your protocol, and if it returns something that is not empty, then it will stop the execution. It will not even launch. And a milder condition is the warnings. So in the warnings, sometimes you may execute, but probably this is not the best condition to execute. So for instance, this is borrowed from 2D classification. So in 2D classification, if the sampling rate is smaller than 3, probably your images are very large, it will take a lot of time. Actually, you don't need that very high resolution to perform the 2D classification. You can do it, but it is not so convenient. So you give a warning. So in the validation, the protocol is stopped, so it doesn't launch. In the warnings, the user is given a window where he sees or she sees the warning message, and then she can decide or he can decide whether to proceed with a step or not, with the protocol or not. So in conclusions, so to create a protocol, what you need is to create the protocol file, change the class name, write the help, and write the label. Then you register this protocol in the init.py of the protocols folder, and you have also to register into the left menu that is done in the protocols.conf. Then you design your user form, you create your execution plan, you create your functions, and then the last step should always be to create the output. In very rare cases, you don't have an output, but normally you want your function or your protocol to be in the middle of a workflow, so that the output of your protocol is the input of the next one. And then you have to create all these support functions for creating summaries, to create validations, to give to write the methods, or to give warnings, or whatever. So this would be all, and see you in the next video that is about how to create a viewer for your protocol if you need it.